This video uses the results from previous videos in this series to produce a parametric plot of the motion of a massless particle, such as a photon, in the equatorial plane of a Kerr black hole using a Mathematica notebook, which can be found in its original form at this website here. It's written for the Schwarzschild geometry, but with modification, it can handle the Kerr case. Now, that modified version I'll include in the notes section of this channel, so the notebook you can find there. This particular notebook comes with the book Introduction to Einstein's Relativity by James Hartle. It's an excellent book, so please do go have a look at that. Right, and the actual file will look like this, being modified. And it comes, it's related to James Hartle's books Gravity and Introduction to Einstein's General Relativity, but you have to modify a few things. So key quantities will be the angular momentum, L in this case. The substitution of the variable u equals 1 and r is used throughout, and I'll be sticking with units of m equals 1, g equals 1, c equals 1, and geometrized units. The energy parameter epsilon is c squared epsilon squared. That's the energy of the orbit in terms of c squared times the energy parameter squared. The starting radius will be RST, number of orbits in orbit. There are some tests for different types of orbits. We're going to, in this video, just be looking at types of orbits photons follow in the equatorial plane of a Kerr black hole. And what you will notice is that there are no bound precessing orbits like we have with massive particles. So particles of mass can enter into bound elliptical or even circular type orbits, and that won't be the case here with massless particles, but you will see other orbits, scattering, deflection type orbits, and I'll show you a couple of interesting ones. Now, so starting with all that, the A star is the dimensionless spin parameter. A is gm on c squared times the A star. Gm and c are all set to 1 for this, so we're talking about angular momentum. For cases for particles with mass, it's angular momentum per unit of mass, but with massless particles that doesn't apply, but we're still setting G, M and C to 1 here. So you need to specify the effective potential, and we've derived all that in previous videos. I'll just run through that again, just remind us of that in a moment. So here's for an example of angular momentum set to 3.66062 units. Plot the effective potential, then set the energy of the orbit, 1.5 in this case, and that gives us here. So we have the energy, the maximum value of the effective potential is less than the energy in this particular case, and it will produce a certain type of orbit for us. This sets the starting point. I've set that quite a unit away. That's RST of 215, which means 250 gm on c squared, or just 215 when gm and c are set to 1. Sensitivity parameter, set like 10 to the minus 14. That's just me being ambitious. Then some tests for different types of orbits, because this same program with a different effective potential can deal with particles with mass. Whereas this video is focused on the particles without mass, the massless case like photons, gravitons, and maybe some neutrinos. So the integrand here, which I'll pick up on another page, but anyway, just get to the crux of that. This particular example here, setting, now these two blue circles, this is the outer event horizon for a given spin parameter, and this is the inner event horizon. The only thing with this model is that when we come, yes, we can have photons crossing the outer event horizon, but the program really only goes to about here, to this point here. It can't go any further in. That's because the approximations that were made. If you look at the previous video, the one immediately prior to, there are some approximations made, so that the approximations are really valid for distances outside the event horizon. Once we get inside to the smaller distances, though, the model's not so effective. And you need to see the previous video for that. Okay, so here's our photon coming in here, crossing the event horizon, and so on. Anyway, so let's go back to where we meant to be. Here we are. So for previous videos, the equation of motion for massless particles in the equatorial plane of a Kerr black hole was found to be this equation of motion. Now, we rearranged that a bit, but made the substitution R as 1 on U, but when we did that, we left this constant term on the right, and we took these two terms here, second and third term, over to the left-hand side. Then we made the substitution R as 1 on U. And here's our effective potential for a massless particle. Next, if we're going to plot the particle in the horizontal equatorial plane, then we want to find the total change in the azimuthal angle phi, and we found that to be given by this approximation between 2 points U1 and U2, and U1 is far out, U1 is close in, U2, sorry, close in, and we wanted this total change of angle. Then the final step was to parametrically plot this. So imagine it's projected onto the equatorial plane, onto the horizontal plane, and the plot was made in oblate spheroidal coordinates, of course, because you've got the spin, okay, which causes the black hole to bulge at the equatorial plane. And so plotting in that plane, the plot you just saw earlier. Okay, now let's look at some examples. I'm going to look at the prograde and retrograde case for each example. So here's a photon with an orbit that has an angular momentum in the same direction as the spin of the black hole. Energy of the orbit, the starting distance, 25 RST, or 25 GM on C squared, starting out here. And I set the parameter. This doesn't need to be set to 10. I'm just overly cautious, overly optimistic maybe. It doesn't need that. 2 would be fine, but anyway, I get carried away. Okay, so here's our effective potential here, and the energy is well above, the total energy of the orbit is well above the maximum of the effective potential here, and it produces this type of orbit where it comes in. Okay, so this is the prograde case. So the photon has angular momentum in the same direction as the spin of the black hole. They're both co-rotating together. Next example is to look at the counter-rotating case or retrograde case. And when we do that, we get totally different effective potential when H is negative value. Same energy, the orbit, but the effective potential is way down here. Same starting point, 25, and then the orbit just comes in from the other side. But this part here, it's a bit flatter because remember the orbit as the black hole, as we're looking from above from the positive Z direction here, is rotating anti-clockwise. And in the previous page, if I just go back, there's a bit more of a curve here in the opposite direction. Just go back. See how it curves a bit more here? The photon is carried a bit further around before entering the event horizon, before crossing the event horizon and going in. Whereas here, in the retrograde case, it crosses over very quickly, okay, because the photon's angular momentum is in the opposite direction to the spin of the black hole. Let's have a look at another example now. I'll keep the same angular momentum for most of these. I'm going to set the energy a little bit lower here, so the maximum of the effective potential, a little bit closer to the energy of the orbit here. Same starting point, and again, it curves around, crosses the event horizon, and comes on in. Let's look at the retrograde case, and very different effective potential, and again, much shorter path in here, flatter, shorter, and much more rapidly enters the outer event horizon, that is. Another example, let's bring down the total energy right to the very tip, maybe slightly above the maximum value for the effective potential. And when we do this for the prograde case, for the co-rotating case, positive angular momentum for the photon, rotating in the same direction, or angular momentum in the same direction as the spin of the black hole, and we can see this wonderful massive scattering orbit here. Massive scattering orbit. Round it goes, and off it goes. Okay, now, by simply putting a minus sign here, considering the retrograde case, and same energy, same starting point, number of orbits the same, have a look what we get now. Very different effective potential, and very much shorter path in, and no deflection, no scattering away, straight into the event, straight across the outer event horizon, straight in. Very different type of orbit there. All right, next one. Let's just come again near the maximum value here, but we're going to have a different angular momentum this time, different energy, but very, very close. I think almost on from memory, I can't remember. But very, very close here to the tip of the maximum potential. And we notice here that the orbit comes in, round it goes, bang. Let's have a look at the negative case now. Here's negative, and none of this curling around. So much quicker path in, much more direct path in across the event horizon. There's the effective potential here, very much below the total energy of the orbit, which was the same as in the previous case. Simply changing H affects the effective potential considerably and the type of orbit you get. All right, let's have a look at now. We're going to start closer in now. Instead of starting out at 25 units, we're going to start out at 5 units GM on C squared. And we produce this nice, lovely plunge orbit coming in. Okay, there's the effective potential just on the very tip, at the tip of the maximum effective potential. That's the total energy of the orbit is equal to the maximum effective potential there. And you can see how it comes around. Beautiful looking orbit, spiraling in. Now, let's have a look. Remember the point here where the energy equals the maximum effective potential, you get those unstable circular orbit. Unstable in the sense it just spirals in. Next on the negative case, much more direct path across the event horizon. Okay, because the black hole is rotating anti-clockwise as you're looking at the screen here, anti-clockwise, and the angular momentum of the photon is clockwise. Much shorter path. Effective potential, everything is different. Same energy, same starting point, everything. All right, another one, another scattering orbit. This one here, just a touch below the maximum effect. The energy here, E, is just a touch below the maximum effective potential. You can just see it on the screen there. It's a bit below. And it starts on the right here, out at 25, which I've cut off from the screen here, and comes in, round it goes, anti-clockwise, and comes out here like that. Okay, now have a look at the next one now. When we put a negative in front here, we give the photon the angular momentum in the opposite direction. Whoa, again, much more direct path across the event horizon, totally different effective potential, everything. So we'll keep going. Another scattering orbit here. E is 1. Now the total energy is set quite a bit below the maximum effective potential, and we get this scattering orbit starting on the right here, starting at 25, which I've cut off here just to make the plot more visually appealing. Comes in from the right, round it goes. Now we'll have a look at negative case. And again, look, very much direct path in, totally different effective potential. Next example, lowered the energy considerably below, halfway down the maximum, below the maximum effective potential, quite a bit down. And here we get this deflection orbit this way. Same starting point, 25 units out here. Let's look at negative case. And negative case, a little bit of a spiral in there, but again, totally different to the previous picture. That's the effect of the spin of the black hole itself, twisting the space-time around itself. All right, here's another one. Okay, the energy is much lower now. And we can see it just scatters it, deflects it from its orbit. Just deflects it more than scatters it, actually. Deflects it. Now let's look at negative case. Oh, quite similar. Quite similar. Okay, and the effective potential, well, the effective potential, the plot is lower, but still similar to the previous one. Let's keep going. Here's another one now. Set the energy very low, and here it deflects it to some degree, a very small amount. And the negative case, very similar. Let's just keep going. There's some more examples to look at. Okay, higher angular momentum this time, higher energy. Okay, but it's going to start very close, about 1.5. So outside the event horizon for a spinning black hole with spin parameter, dimensionless spin parameter 0.8. Because of course the size of the dimensionless spin parameter will affect the radii of the event horizons. All right, so starting very close, crosses very, very quickly. This continues, but just this is where the approximation made in this series breaks down for the small r values. If you look at the previous video, you'll see why there were two terms, a 1 over r term and a 1 over r squared term, which for large r you could ignore, but once you get for very small r, they become significant. And they're out of this model. They're not included in this model. As an approximation, they were removed. Okay, so crosses the event horizon, so that's the prograde case. Retrograde crosses more quickly. All right, let's have a look at another one. And again, starting a little further out, again, quite a quick trip. It falls back in very, very quickly. You notice the total energy up here is well above the maximum effective potential. Falls in very quickly, and as you might imagine, the negative retrograde case, where H is negative here, it'll fall in more quickly. And so it does. All right, and I think that's it.